All right, so previously we talked about how a unit step function is ideally going to transition from 0 to 1 instantaneously, but in practicality, that's not the case. It's actually going to be modeled more as sort of a ramp here, where there is some time, delta t, associated with this rising edge centered around 0, right? Maybe it's very, very narrow, very steep slope. Maybe it's not, but nonetheless, there's going to be some delta t there. And so what we can do is we can actually model that rise pretty similarly to the way that we modeled the delta function. And we can say that that rise starts at negative epsilon and goes till some time epsilon. And it has a slope, of course. It's going to be the rise over the run, which in this case, the rise is 1, right? Value of 1. And the run here is going to be 2 epsilon. So my slope of this linear ramp is 1 over 2 epsilon, right? We can see that from basic algebra. And so, let me just erase that now. And so maybe you're starting to see how the unit step function and the delta function are related. Maybe you're not, but let's just take a look. So if I am looking at the unit step function here, and let's say I want to analyze the slope of the unit step function. Okay, so from basically negative infinity up to negative epsilon, the slope is 0. From epsilon out to positive infinity, the slope is also 0. And then during this one segment from epsilon or negative epsilon to epsilon, I get a slope of 1 over 2 epsilon, right here. And so, again, as we talked about, that epsilon value, if it gets really, 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 really tiny, in this case, if it gets really, really tiny, we're basically making this pulse bigger and bigger. In this case, if it gets really, really tiny, not only are we making this rising edge a lot faster, but we're also making this slope a lot greater, right? Because the slope is 1 over 2 epsilon. If epsilon gets small, then the slope gets really, really large until the ideal case, which is infinite slope right at this point, right? That would be infinite slope if I have an instantaneous change in the y direction, because again, slope is basically equal to my change in y divided by my change in the x direction. So in this case, if my change in the x direction is 0, or basically instantaneous, my slope blows up to infinity, right? And so let's take a look at this delta function now. This delta function, so let's write that out again. The slope of u of t, or basically the derivative of u of t with respect to t, we just said basically it's going to be 0 from negative infinity up to epsilon, and also from, or negative epsilon, and also from positive epsilon out to infinity. And then it's basically going to be 1 over 2 epsilon from negative epsilon to epsilon. Well, what is this function right here? It's 0 from negative infinity up to negative epsilon. It's also 0 from epsilon out to negative infinity. And then it's 1 over 2 epsilon from negative epsilon to epsilon. That's literally this function. And so that is proof that we can say that the derivative with respect to time of the unit step function is equal to the unit impulse function. And that is how the two are related. The unit impulse function is the derivative of the unit step function. And even more specifically, the unit impulse function is the derivative of the unit step function for these two cases when we let epsilon go to 0. So at the limit as epsilon goes to 0, of course, we get an infinite slope, right? We get an infinite slope at one particular point. In this case, it's going to be at time t equals 0. And that's exactly what we see from the delta function. If you recall, the delta function is 0 everywhere, basically t not equal to 0, and it's infinite at t equals 0. Well, what is the slope of the unit step function? If I look at the unit step function again, it goes just like this. The slope here is 0, the slope here is 0, and the slope here, right at t equals 0, is infinite. And that is the delta function. And so that is the proof right here that the delta function is the slope of the unit step function. And it goes both ways. Of course, we could also look at the integral of the delta function. So if we take the integral of this delta function, we're moving along. Oh, let's look at the ideal one. We've got 0, 0, 0, 0, 0. We take this integral, and then from there on the integral, or sorry, let me draw a delta function. I need to draw a delta function. So let's draw a delta function. We're taking the integral 0, 0, 0, 0, 0, 0, 0. We get to this point. We know the integral under one of these spikes is 1, and then we keep integrating 0, 0, 0, 0, 0. So we stay from negative infinity to infinity. The integral of this is a value of 1, right? And that's exactly what we see in the unit step function, right? If we take the integral of this unit step function, we basically get u of t is equal to 0 for t less than 0 and 1 for t greater than or equal to 0. And that is the integral of the delta function, because if we look at our integral of our delta function, again, it's 0 for all time t less than 0, and then for t greater than or equal to 0, the integral, basically the total area, jumps up to a value of 1 at this instant in time, and then it's just going to remain 1 for all time after that, because that is the total area under the curve as I continue to integrate, because all of this is 0. If you have any questions about this, obviously, please feel free to let me know. I just wanted to touch on these. I think they're important. Again, they're going to become even more important in EE 360. They're going to show up in this class as we move through this module, so I definitely needed to talk about them and how they're related. And this is kind of the key here, is that the slope of the unit step function is the impulse function. The impulse function's integral is the unit step function by definition, okay? So I'm gonna go ahead and end this video here. That's all for unit step and unit impulse functions, and we're gonna start talking about Laplace transforms in the next video.